Hi, Assalamualaikum everyone. So now let's proceed with our next subtopic in frequency response. So now let's proceed with sketching the Bode plot. Okay, now we know that the Bode plot is a useful tool that is used to show the gain and phase response of the linear time invariant system. And plot diagram must consist of two plots, that is a magnitude plot and also the phase plot. So now let's see how we need to plot the Bode plot on the semi-log graph. Firstly, okay, so now to plot the Bode plot on the semi-log graph paper, so you need to justify the axis. Firstly, that the x-axis is used to represent the frequency and the y-axis is used to represent the magnitude. So the scale of the semi-log graph, firstly you need to justify for each 2 cm its mass is equal to the 20 dB, which is 1 boxes of this semi-log. And for the x-axis, so 1 decade, we will start from the frequency or the corner frequency with 0.1 and up to 1, 10, 100, 1000, 10,000 and 100,000. So for each increment is used to represent the 1 decade. Okay, so same as goes to the phase. So for 2 cm, scale is used to represent 45 degree. And one more thing, please bear that for every 0 dB, it must similar to the 180 degree line. So then you can plot the magnitude plot and the phase plot on the same semi-log graph paper. But in case you want to separate the plot, it is no problem to do that. Okay, so the plot of the Bode plot, we have point which shows the increment of or decrement of the slope. So this is the cut-off frequency, or also known as a corner frequency. So there are positive slope and negative slope in the Bode plot. So now let's see the rules in plotting the Bode plot in the semi-log graph paper. So this is the poles and zero in the transfer function. So for each positive and negative poles will represent the positive and negative slope. For example, this is S, or known as derivative. So it is used to represent the positive 20 dB. Same as the phase, which is positive 90 degree. And for the 1 over S, it is an integral part, which will represent the minus 20 dB and minus 90 degrees. So this point will represent, or will be used as the starting point. So now we have a first order and second order. For the first order of the zeros, so it is used to represent 20 dB slope, and the negative or the poles is used to represent the minus 20 dB slope. Same for the phase slope. For the second order or quadratic, so the zeros, the transfer function of the zeros is used to represent positive 40 dB, and the poles is represent the minus 40 dB. So how we sketch it, the positive and negative dB in Bode plot. So now let's see, this is the semi-log graph paper. So first, as I mentioned, that we need to justify the scale of the x-axis, where 1 boxes or 2 cm is represent 1 decade. So we will start from 0.1, and for this 40 dB, it need to plot from 0 point or any point in the corner frequency, and it must end at the end decade, or at the decade of 10 with 40 dB scale. So this is used to represent positive 40 dB, the same as positive 19 degree per decade. Same as 20 dB. So for positive 20 dB, it will take only 1 boxes or 2 cm per decade, and it will stop here. This is positive 20 dB. Same as the negative part of the slope. So for 1 decade, it will decrease for only 1 boxes. While for the minus 40 dB, it will take 2 part, because this 2 part is represent 40 dB, and it will stop here. Okay. So now let's see example from the final paper, June 2012, which is we need to sketch the Bode plot by assuming that k is equal to 1, and we need to start the Bode plot with the corner frequency at 0.1 radian per second, and this is the transfer function of the system. So we can see that we have here first order. We have the we have here is integral part, and this is the second order. Okay, so now firstly you need to convert from the S domain of the transfer function to the J omega domain. So for every S domain, this is first order, and this is the integral part, or 1 over S, and this is the second order. So substitute all the S with the J omega, and we will get the answer like this. So next, take out the 60 value like here, and hundreds value here, and this second order is 36. So take out the 36 here. So it will become like this equation. So next, simplify all the equations, and finally you will get this type of conversion in J omega. So we can see that this is the first order, and this is the integral part, or 1 over J omega, and this is the second order part. So now, secondly, you need to find starting point for the magnitude and phase before Bode plot. Okay, so as to find the magnitude, so you need to substitute all the omega here in this equation into 0.1, and you will get 10,000. Then convert this value to decibel, so you will get 80 dB. So the starting of the magnitude will start at 80 dB point. While for the phase, since in this equation we have an integral part is 1 over S or 1 over J omega, which is here. So the starting of the phase plot is at minus 90 degree. This will be fixed at minus 90 degree if it has the integral part. Please use the table to tabulate for each slope for each vector. Okay, now from the conversion of the transfer function into J omega domain, so we tableize all the vector. For example, so this is gain k, it has no slope, and secondly integral. So as the integral, we will start to identify the corner frequency for each magnitude. So how you find this corner frequency? Firstly, look at the transfer function. Okay, so this is the lowest corner frequency, 6, and the second lowest is okay, for this second order, the lowest frequency is 6, and this first order is 60, and the third one is 100. So we have 3 corner frequency, that is 6, 60 and 100. So this is where we want to plot the corner frequency for the magnitude part. So you can verify or you can state the corner frequency for each magnitude point as 6, 60 and 100. So now look at the first integral part, which is, we will start with the first integral part, that is the slope is minus 20. So fill up all the magnitude magnitude slope as minus 20. And secondly, the second lowest corner frequency 6 is coming from the second order. So we will start next after the corner frequency for minus 40. Next is the first order with the corner frequency 60, which is, this is the positive 20 dB. And lastly, we have the poles, which is 100 at the 100 corner frequency. So we will have the slope as minus 20, and sum of all these magnitudes, so you will get like the total slope. So this is minus 20, and this is minus 60, and this is 40, and finally minus 60. Okay, for the phase plot, you need to take 3 decades of the corner frequency. Okay, for example, for this corner frequency 6, you need to take before one step or 1 decade before and 1 decade after. So you need to take 0.6, 6 and 60. While for the value of 60, you will need to take 6, 60 and 600. For the 100, you will need to take 1 decade below, that is 10, 100 and 1000. So now, to fill up the degree for each factor, so we know that integral has no slope, and integral has no slope. And for the second order, okay, for second order is minus 90 degree. Okay, so it will start from 0.6 to 60, 0.6 to 60. Then for 60, it will start from 6 to 600, 6 to 600, and finally for the factor of this one, it will start from 10 here, 10 to 1000, and you can sum or total all the phase, so you will get as this result. Okay, so this total we will use to plot in the Bode plot. So now let's see how to sketch the magnitude plot on the Bode plot. So as we find out just now that this magnitude plot must start at 80 dB with this following slope to be sketched. So now 80 dB is somewhere here. Okay, so firstly I will show how to sketch the magnitude part, and the starting point is 80 dB, which is here. So this is the point. Okay, so now secondly, is the corner frequency from 0 to 6. 6 is somewhere here. So the slope is minus 20 dB. Okay, so minus 20 dB is, we take 1 decade from here, it will be this line to here. So this is the 20 dB line, and it will continue to the corner frequency 6 and will stop here from 0.1 to 6. So next is from 6 to 60, the slope is minus 60. So from 6 here to 60, 60 is somewhere here in this line. Okay, the slope is minus 60 dB. Minus 60 dB means that you need to go down 3 part. Let's say, for example, from here to here. But we need to adjust the difference of this point. So next, so this is the minus 60 dB, and the third one is minus 40 dB from 60 to 100. 60 to 100 is only this point. So, but we need to take 1 decade. 1 decade is mean from here to here. Then we will take only this point from 60 to 100. Okay, next is minus 60 dB from 100 to 1000. So this is the point where 60 dB from 100 to 1000. And this is the overall sketch of the Bode for magnitude plot. Okay, so in order to find the gain margin, so we need to start from level of 0 dB and take to the point where it intersects at the magnitude diagram. So this is about somewhere here 45 dB. So the gain margin is 0 minus 45. So we will get the gain margin as minus 45 dB. So now let's see the phase plot, same as the magnitude plot, and we will sketch the phase plot. So now the starting point of this phase plot is minus 90 degree because we have an integral part which is here in this transfer function. So now minus 90 degree is somewhere here. Okay, so again the corner frequency, we have 3 decades or 3 values for each factor. Okay, so we will start from 0.6. 0.6 is somewhere here. Okay, we will start from here. So from here there is a slope according to this value. So from 0.6 to 6 we will have minus 90 degree. So now let's first see starting from starting point from the minus 90 degree, we have 0, and then next 0.6 to 6 we have minus 90 degree per decade. Next we have 45 degree from 6 to 10, but we need to sketch it in 1 decade to have minus 45 degree. Only we take from 6 to 10. Then next is from 10 to 60, we have on the minus 90 degree. Okay, so we take only 10 to 60. Next is 60 to 100. 60 to 100 is 0. 60 to 600. And 600 to 1000 is minus 45 degree. So this is the pattern of the phase plot. So now how to find the phase margin? So we need to level at the 180 degree point, and we find where this point is intersect at the board or at the plot of the phase. So this is somewhere about minus, here is minus 40.75 degree. So to get the phase margin, 180 we minus 50 by 240.75 degree. So we will get the phase margin is minus negative 60.75 degree. And this is where the corner frequency of the phase plot. Okay, so in order to find the gain margin and phase margin, so just now we get the gain margin and phase margin, then we can find the stability of the system. So as mentioned here, the system is stable if both gain margin and phase margin are to be positive value. So this is the positive value of gain and phase margin. So since we get the gain margin negative value and phase margin negative value, so the system is unstable. Okay, so from this unstable system, we need, in the next chapter, you need to design the compensator so that we can change the system to be stable. Okay, so that's all for now, and thank you.